Good morning.
Good morning.
Everybody's doing well. Looking forward to Friday. It is hump day, so that's a good thing. Before we jump in, anybody got any questions?
Recording in progress.
All right, no questions. Let's do some work. We're gonna continue our discussion on pKa. Also, those of you who are on the, if you haven't checked your announcements, make sure you check it if you're in the Wednesday lab. The people who were scheduled to come last week, it's the same people this week, but just check it and make sure you got all the information. Make sure you get that Zoom link and save it, because it's gonna be the same link every time we meet in that hybrid fashion. So double check today. I sent an announcement out on Monday with all the information you'll need for the lab. So double check, go ahead and get the data sheet. So you can have that and start filling it in. And yeah, yesterday's lab, I think we were there for like about an hour and a half or somewhere like that. Today will be quicker because it's already prepped from yesterday. So, but we're looking forward to it. All right, back to chemistry, organic, lecture, not lab. Right. So we're gonna go back. We talked yesterday about the factors that affect pKa. We're gonna do a bunch of those examples later today. But right now, I want to do a couple of things. I want to take a little bit of time on these examples, and let me do this. Let me cut this out so I can put some room down here. Let me wipe this out. That way we can have some room to work. All right. So it says in this example, let me put the date up here real quick. Today's the 15th. All right. So it says apply the arrows in the following acid-base reactions. So in order to do that, we have to know which is the acid and which is the base. We also have to know how electrons flow from acid. I'm sorry, from base to acid. All right. So we can't do just apply the arrows until we first identify what the acid is and what the base is. And I also want to add another layer to this. I want to use this as another example of predicting equilibrium. So while we're working through the arrows, somebody look up the pKa for water, and somebody look up the pKa for cyclohexanol. And it's cyclo because, again, I'm not going to just, we'll have a section on nomenclature later, but it's cyclo because of the ring, hex because it's 6 carbons in the ring, and then all because it's an alcohol. All right. So somebody look up the pKa for water.
15.7.
Says 16 point.
15.7.
Okay, so 15.7. Okay, great. And then cyclohexanol, anybody got that?
16.
You say 16?
16.
Is that right?
Yes.
All right. All right. So now let me put some electrons in. So of these two, which do you think is the base and which do you think is the acid?
Is the water the acid?
Yes. Very good. Water is tricky because it can be both, but in this case, it's acting as an acid. And when you compare the two molecules, you see that the cyclohexanol anion has a negative charge. It's got 3 lone pairs. So that's going to be more apt to donate a pair of electrons and do proton transfer than water, which is neutral. All right. So arrow-wise, how does this work? If you watch that acid-base video, the first one that I sent, what direction do this is also preparation for the next section, which is nucleophiles and electrophiles. So it's really the same, again, same ideas, same concepts, just different terminology, right? So if this is your base, the electrons are going to flow from base to proton, right? Notice where my arrow stopped. It did not stop on oxygen. It didn't stop between the O and the H. It stopped on hydrogen. That means that that's the atom that I'm attacking and donating electrons to, right? And it's
I have a
double
question.
headed. So that means I'm giving 2 electrons to that hydrogen. And then by the same token, I'm going to break this OH bond and give those electrons to oxygen. Are we okay with that?
I have a question.
Go ahead.
Does it matter which lone pair is donated
No,
from the oxygen? Okay.
no, it doesn't. That's a great question. All right. And now, excuse me, look at the other side. You can see the result, right? The oxygen, which was here, picked up a proton, didn't it? So now on the other side, it's an OH. And then the water, which was over here, lost a proton. You see that? And then let me put in an extra lone pair. There. Right? All your acid-base reactions are going to have that same flow of electrons. Electrons are going to flow from a lone pair on the base towards a proton on the acid. And then you're going to break the bond between the proton and whatever atom is bonded to. And those electrons are going to go back to that atom. There's a reason why this happens, right? If you think about an OH bond, how would that be polarized? Think back now to when we talk about dipoles. How would the OH bond be polarized? Would it be towards hydrogen or towards oxygen?
Towards
Oxygen?
Towards oxygen, right? The polarity is based on electronegativity, is that right?
yes.
So if the bond is whatever atom the bond is polarized towards, that's the direction the electrons are going to flow when you break that bond. They always go back to the more electronegative atom. Right? Always go back to the more electronegative atom. All right. So now we got that. We see that. Which way will equilibrium favor?
Is it the cyclohexanol?
Yes. Equilibrium is going to be favored in this direction. Very good. Who was that?
Tia?
Nice work. Nice work. All right. So equilibrium is going to be toward the weaker acid. Now it's not much weaker because we've done problems like this where the gap between the two acid, the acid and the conjugate acid has been huge. Here, if we ask how much more acidic is water than cyclohexanol, what would you say?
That is not very much more acidic.
Yeah, but we can be more specific than that, right? We got an equation. What's the difference in pKa?
0.3.
0.3. What's the number of times more acidic? How do we calculate that? Wouldn't it just be 10 to the difference in the pKa? Is that right?
Yes. I have a question.
Go ahead. Go ahead.
Why did you, can you scroll up when you're done?
Mhm.
Why did you write those arrows the way you did?
Okay, so it's an equilibrium, which means that the reaction can go forward or backwards. Is that right?
Right.
Well, we said the forward reaction towards cyclohexanol is favored because that's a weaker acid. So the reaction arrow going forward is going to be bigger because that reaction is favored, as opposed to going backwards. See how the shorter arrows on the bottom pointing backwards?
Mm-hmm.
That's because that to go backwards is not favored.
Okay.
All right, that's a great question. Right, so we know that we got a little toolbox now we can work with these acids and bases, right? We should be a little better at pushing the arrows. We also should be a little bit better at determining how much more acidic the acid and the conjugate acid, the difference in acidity between those two. And we also should be a little bit better at predicting equilibrium. So the more we do, the better we're going to get. You got to stay engaged so that everything that I'm giving you can get, and everything that I'm laying down you can pick up. All right, so let's do the next one.
When you say acidity, you mean based off of the pKa values? Because I seen there, I think in the book, there was like a difference between acidity and the hydrogens.
Yeah, well, that's a little bit different if you're thinking about pH versus pKa. The pH is dealing with hydrogen ion concentration.
Okay.
But the pKa is a little bit different. It's not really dealing with proton concentration, more so than it is with what the conjugate base looks like and how stable it is.
Okay. So we just need to know about the pKa differences.
Yes. Yeah.
Okay.
Yeah, we're not really going to touch pH.
For the exam, will you give us the pKa values?
Yes.
Okay.
Yeah, you'll have a table it's going to be embedded in the instructions. It'll have a list of pKa's and all that stuff. So any acid that you have on the test, you'll be able to look up the pKa.
Is it the same table from the textbook?
No.
Oh.
It's probably a different, I probably took it from a different book, or I may have taken it from a different source. So it won't be the exact same as what's in the book. That's a great reference though. All right, let's do the next one. Next problem. We're gonna do the same thing. We'll put the arrows in. We're gonna figure out the equilibrium, and yeah, so let's do this problem. Let me throw some electrons in here. All right, that's that. And then over here, that's sloppy, sorry. Even worse. We'll get it together one day. So somebody look up the pKa for 1 butanol. It's 1 because of what an alcohol is on the first carbon, but because there are 4 carbons in the chain, and all because it's an alcohol. So 1 butanol. And then somebody look up the pKa for 1, 2, 3, 4. I don't need to put a 1 in there. Butane thiol. It's thiol because of the sulfur, right? It's a thiol is a sulfur analog of an alcohol. All right, so that's why it's butane thiol. Butane because it's 4 carbons in the chain, and thiol because it's a sulfur analog of an alcohol. Right, so somebody look up the pKa for that.
10.2.
Anybody got it?
10.2.
10.2. Okay, great. We're going to use that too, that information, because now we can, with the difference being so huge, we can talk about why. We can go back to our factors that affect pKa, because I'm sure butanol, 1-butanol is somewhere about 16 or 17. Am I right?
Yeah, 16.95.
Right. So there's a gap. There's a gap of almost 7. In this case, it'll be 7, 10 to the 7th is the difference in pKa. All right, so let's do that. So X equals 10 to the difference in pKa. This is going to tell me how much more acidic one is than the other. And then so I'm just going to round up to 10 to the 7th. Which side is going to be favored in equilibrium?
The right side.
The product side. Good. Over here. And are we okay with the equilibrium arrows, what they represent? It means that the forward reaction is going to be more favorable than the reverse reaction in the equilibrium. We okay with that?
Yes.
Yes.
Let's put some arrows in. Where do we start? Look at the 2 species that you're dealing with. Which one do you think is the base and which one do you think is the acid?
The butanol is the acid.
Butane thiol, yes. Right, and just as a rule of thumb, if you have an alcohol present in any reaction, more than likely it's going to act as an acid, because all of your alcohols are acidic. They're not overly acidic, they're not strong acids, but they are considered acidic. So if you have an OH hydroxyl group, that group can be considered acidic unless it's in the presence of a proton, which case it'll probably do proton transfer and act as a base. But 99% of the time, an OH or an SH group is going to be considered acidic. All right. So this is my acid. This is my base. On the other side, what would this be? Conjugate base or conjugate acid?
Conjugate base.
Good. That's my conjugate base. This is my conjugate acid. Remember, the conjugate base is what the acid becomes after it loses a proton, and the conjugate acid is what the base becomes after it gains a proton. So let's put the arrows in. And let me wipe this out so I can draw the SH bond out, make it look better. Okay. So somebody tell me what arrows I need. Help me out.
One of the lone pairs from the oxygen is going to go to the H. Then the
Right.
bond between the S and the H is going to go to the S as a pair of lone pair.
Great, excellent. Who was that?
Gosh.
Nice work. Thank you. So I'm going from here to here. Is that right? And I'm going from here to sulfur. Yes. Remember, the electron, when I break that SH bond, sulfur is more electronegative. So the electrons are going to that atom always. That rule you need to remember, especially for the next section, because you're going to see this motif a lot. When you have nucleophiles and electrophiles and things like that, you're going to see that motif a lot where you end up breaking a bond and you got to figure out which bond, which atom in the bond gets the electrons, right? It's always the more electronegative atom. Right, so that you can see the difference over here. You see you have a SH. It didn't highlight the white part, but you got it. And then that lost a proton, so now I have a sulfur on the other side with a negative charge, and then you can see the oxygen here. On the other side, it's an OH. All right, now let's answer this question. Because we said that the sulfur had a pKa, the thiol had a pKa of 10.2, and the oxygen had a pKa, the butanol had a pKa of 16. So that's a huge difference, right? The difference in pKa is a roughly 7. I rounded up, right? So why?
I know the sulfur has a larger area to take. I think it's something with the size of sulfur.
Okay, great. Is that Sanaya?
Yeah.
Very good. The sulfur has a larger atomic radius. Now, here's the thing. Oxygen is more electronegative. Am I right? Will you stop flipping?
Yes.
Sorry.
Yes.
Oxygen has electronegativity, and it's above sulfur, right? Of 3.5. And sulfur, I'm not sure what the exact number is. Can somebody look that up, what the electronegativity is?
$2.58.
2.58?
Mm-hmm.
Okay. So the electronegativity, in this case, is not stabilizing the negative charge on oxygen as opposed to sulfur, right? You see sulfur is negative on the other side. But that negative charge on sulfur is more stable. They're both sp3 hybridized. So hybridization is not a factor of stabilization. Right, they're both sp3. Do you agree? Got 3 lone pairs around it and 1 bond, so 4 groups on each one. Induction, not a factor. There's nothing close by that negative charge in either the base or the conjugate base that's going to help to stabilize it. There's no electronegative functional groups, no carbonyls, no fluorines, nothing. They cannot do resonance. Right, so it's going to come down to these 2 factors, electronegativity and size. And I think in one of the videos that compared size and electronegativity, the size is more stabilizing, right? What is it about the size of the sulfur atom that allows it to stabilize the charge more? And when we talk about size, what do we mean? Are we talking about what specific characteristic of that atom are we dealing with when we talk about how big it is? Anybody remember that?
We're talking about the radius.
The atomic radius, right? So sulfur has a higher atomic radius, right? What that means, what's the goal again? To delocalize the charge, right? Either through hybridization, which is attached to electronegativity, through the size or through induction, some kind of way, take that charge and spread it out so that it's not concentrated. And so a larger atomic radius means that you're able to delocalize that charge more through by it being dispersed over a larger surface area.
How is size more stabilizing than
Well,
the other one?
yeah, so let's think about it. If something is more electronegative, that means it's more desirous of electrons. So it really comes down to, and this is a theory that we never discussed, but I can introduce you to it. It really comes down to whether or not the atom is what we call hard or soft. So a hard atom is a little smaller and the charge is more concentrated, right? And then a soft atom is bigger and the charge is less concentrated. So that if the charge is more spread out and less concentrated, that's a good thing. All right, so that's how size is more stabilizing than electronegativity, because the more you can spread that charge out, the more diffuse it is and the less concentrated it is. So that makes that atom that's holding that charge more stable, if that makes sense.
Thank you.
So sulfur will be considered like soft. And then, so soft means like in terms of, if I had to give you an analogy, it would be like a dandelion versus a marble. Like marbles are really hard and dense, and then dandelions are not so much, right? You know, they're kind of fluffy and more spread out. Wind blows and those little, the parts of the dandelion just blow away, right? So sulfur is more like a dandelion. So it's a bigger surface and the charge is more diffuse. Go ahead, I see two hands. I saw two hands up.
So what is the, go ahead, T.
So like, what if you have two atoms that are on the same principal level? How would you determine that?
It would depend on what the atoms were. And it would depend, we just have to go through the factors one by one. Right? If there's nothing to distinguish them, well, there's got to be something. But the acidity difference, like up top, that's why the acidity difference is not that much greater between water and cyclohexanol, right? It's only 0.3, because there's really nothing that distinguishes those two things from one another, right? If I had to take a guess, I would say that the cyclohexanol, the anion, which is the base up there on the left side, because of all those all the carbons in the ring, those are actually slightly destabilizing, right? And so that's why the pKa is a little bit lower, because when you put that negative charge on oxygen, you got all those electron-rich carbons around oxygen, that's going to slightly destabilize that, slightly, right? As opposed to water, which doesn't have those carbons attached to it, so they're not donating any electron density towards it. All right, but yeah, it's a case-by-case basis, and it's very nuanced. So depending on what the conditions are, that's going to help us to determine like which factors play a role and which ones don't. Did that answer your question?
It did.
Okay, all right, go ahead. I know that was a second question too.
So with the size, like on the periodic table, what was the trend for knowing if
It's left to right and top to bottom. And I think there's one exception. I think nitrogen is kind of an exception, and it's because of its electron configuration. But when we come to an example with nitrogen, we'll discuss that and deal with it. Yeah, but the atomic radius increases from left to right and across a period and from top to bottom in a group. All right, let's go to some other problems. Let's do, now I'll highlight them because I know that pink is gonna throw you off, but I'll highlight the ones that we're gonna do. So we're gonna go here. And we're gonna work through A, D, G, and let's work through those. So I'm gonna copy this and put it on another page. And we're gonna do the same thing. We're gonna predict the products. We're gonna put the arrows in. We're gonna discuss the equilibrium, and we're gonna discuss the differences in pKa. So we'll lump in all of our skills, and the more we do, the better we're gonna get. Let me add a page in here. Right. Uh-oh. All right, so let's take the first one, which is sulfuric acid. I'm actually going to draw that out so you can see what the structure looks like. So this is S, this is A. So that's sulfuric acid, and then this is the acetate anion. So I'm going to draw that out. I think we talked about that the other day. All right. And then shrink that down some. So let's put the arrows in. Actually, let me flip this around and make this easier to see. All right, so this is my acid. This is my base. All right, and then so let's put the arrows in. Where are the arrows going to originate in this example? And again, we're going to do arrows, equilibrium. We're going to talk about pKa, the Pka difference, and
Is arrows the same as mechanism? Because that's what
Yes.
the book says. Okay.
yes, the mechanism is just a step-by-step interpretation of what is going on in a reaction, and you interpret it or you illustrate it by using curved arrows. So yes. Actually, we'll put that here. Right. So what is the mechanism? Like, how do we show that for this reaction? How do we show the base reacting with the acid doing proton transfer?
You draw it from the negative oxygen on the base to hydrogen, and then that bond, the bond between the two goes to oxygen.
Yes. All acid-base chemistry is gonna happen that way. Same arrows, same flow of electrons, base to proton, and then from the proton back to the atom is bonded to. Right, so that's that. So on the other side of that, I'm gonna put a box here because we're gonna predict equilibrium. If I could draw a box.
Why did you donate it to that hydrogen, not the other one?
They're both equally susceptible,
Okay.
but I just picked that one because it's easier to show because it's on that side. But both of those protons are equally susceptible initially to being taken off. And then once you take one off, the pKa of the other one goes down some because the negative charge on oxygen is kind of able to donate and kind of destabilize the second conjugate base. But we'll talk about that when we get to it. All right, but great question. So either one of those right now, I could take one or the other, doesn't matter. So then over on the other side of my arrow, I'm going to get this. Is that right? Yes, no, maybe.
Yes.
Mhm. That plus what? What's my conjugate base gonna look like? Is it gonna look like that?
Yes.
Okay, great. Now, what's the pKa of sulfuric acid? Somebody look that up. Should be pretty low,
-3.
-3. All right, we'll take that, -3. And then what about acetic acid? This is acetic acid.
4.75.
I gotta make room for that, so hold up 1 second. So 4.75, is that right?
Mm-hmm.
Okay, now, we've done the mechanism, we know the pKa's. Which side is equilibrium gonna favor?
The product.
Product side, here. Again, if you ever get confused about it, put the numbers on the seesaw. Right? 4.75, and it's -3 point. Right. Is that right? The negative number is smaller, so the balance on the seesaw is going to favor the larger number. So if you ever get confused about how to predict equilibrium, put the two pKa's on the seesaw, and it's going to tilt toward the bigger number. All right, is that okay?
Yes.
All right, so now here's the question. Here's the other question. So we looked at the mechanism. We know which side equilibrium is going to favor. What's the Pka difference? Will be like 7.75. Is that right?
Yes.
Right. It's the difference between the two pKa's. So 7.75. And you have to just take the absolute value. So it'd be -3 minus 4.75, which would be -7.75. And then I just take the absolute value of that. So then sulfuric acid the difference in acidity or how much more acidic is sulfuric acid than acetic acid, which would be this term X, is 10 raised to the, let's just go ahead and round it up, 10 to the 8. My 8, that 8 is horrific. Sorry. That one's even worse, but it's okay. So it's 10 to the 8 times more acidic. What does that mean for its conjugate base? Anybody?
Does it make it weaker?
The conjugate base? If it's a stronger acid, what does that say about its conjugate base? Is it more stable or less stable than the conjugate base for the other acid?
Is it more stable?
It should be more stable, right? We'll put that here. Okay, so the conjugate base is much more stable. So if we look at the conjugate base for sulfuric acid, which is right here, and we're comparing that to the acetate ion, which is over here, because that would be the conjugate base of acetic acid, even though it's acting as the base here. And we think about the factors that affect pKa. Where is the negative charge in both cases? What atom? What atom is it on? In both cases.
The oxygen?
Oxygen. Good. Right. So right away we can see both oxygens are sp3 hybridized. So we can't compare hybridization because it's on the same atom. The same with the size and electronegativity, because the charge is on oxygen in both cases. Are y'all following that logic?
So why are we looking at oxygen?
That's what a negative charge is. That's what we use to compare the pKa, right? We said it's loosely based on the stability of the conjugate base. So if we're comparing the two acids, sulfuric acid, we see the conjugate base for that right here. Is that right? And then acetic acid, we started with the acetate anion as a base, right? But that's still the conjugate base of acetic acid. So that's what we're comparing when we're looking at or determining why the pKa of acetic acid is what it is and why the pKa of sulfuric acid is what it is. Does that make sense?
Yeah, so we'll always compare the base and the conjugate base.
Yeah. When we're trying to figure out the difference in the pKa, yes. Because again, pKa is loosely based on the stability of the conjugate base. So the negative charges on oxygen in both cases, so hybridization, they're both sp3. They both have the same electronegativity, they're both the same size. There's really no induction. So we can't compare that because there's really not any inductive effect from the sulfur or from the carbonyl. But what can each one of those conjugate bases do?
Resonance forms.
That's the last thing that's left, right? Resonance. So let's compare them real quick, and then we got to stop. All right, let's do that. So this is, sorry. This is the acetate anion. Put that here. That's negative. Versus the sulfuric acid anion. All right. So we did resonance here. Is that right? Is that how we could do that? Or how we would do that? You agree with that resonance form?
Yeah.
Yeah.
What pattern is that?
Is it a lily?
It's a allylic anion. All right, let's go to the sulfuric acid. Let's do, because this is the same pattern. It's an allylic anion. Can we do that? We can do that, can't we?
Yes.
Can we do it again?
Yes.
Is that right? So what can you say about the pKa difference? Why do you think that's such a huge difference?
Is it because sulfuric acid
Mhm.
can do more resonance?
Yes.
So like the charge can be delocalized more.
Come on with it. Yes, that's exactly right. So the conjugate base of sulfuric acid has multiple resonance forms. So when I get excited, my handwriting goes to crap. So the charge is more delocalized. Who was that, by the way?
Yeah.
Yeah. Put your cash app in the chat. I'm gonna buy you lunch today. That was a great explanation.
Thank you.
Mhm. And that's where we're trying to get, right? When you sit through a lecture or discussion, you need to be soaking up all of this stuff, because when you see it on a professional exam, if you're taking the DAT or the PCAT or whatever, they're not going to water it down. They're going to give it to you exactly in the technical jargon that you're reading in the textbook. So it's not going to say the charge is more spread out. It'll say it's more delocalized. So that terminology matters. The better you get at speaking the language, the more that means you have a better command of the material, right? I use a lot of analogies, but I also have to go back and be technical with it too, because that being technical and using the jargon means I got a command of the material. So that's what you want to get to by the end of this class. You want to be able to speak the language as well as understand the concepts and things like that. Speaking the language is a part of the learning process. All right, so this is good. We'll stop here. I know we only got through one example, but we're gonna work through the rest of them on Friday. We're gonna have a breakout session on Friday where I'm gonna turn you loose on a couple of problems, and we're really gonna be done with this section. And then we'll move on to another section on Monday. Test is Friday on Blackboard, open notes, all that good stuff. So yeah. Any questions before we, and I'm not gonna have a chance to post this, the video or the notes yet, because I gotta leave and head up so we can have lab. So just be patient about that, and I'll post it later on this evening.
What exact topics should we expect on the test?
Just if you look at 1A and second module, and look at the learning outcomes, that'll tell you. Because I think with 1A, we did functional groups, we did solubility, we did intermolecular forces, and then we also in 2 was all pKa. So go back and look at those learning objectives, and that'll tell you exactly what you need to be going over for the exam.
Are we turning in all the problems that we have like that we did so far in class?
Yeah, so we're gonna finish up this handout on, might not finish all the problems, but we're gonna finish what we're gonna do by Friday. So you'll be able to turn in this handout, because we'll be done with the problems that I think are gonna help us understand this. And then you'll turn in the intermolecular forces page from 1A, which I'll have to create a new link for. I really should have broken that document down into 2 documents, but I'll get it together. I'll make sure that there's no confusion about what to turn in and where to turn it in.
Okay.
Yep, all right. Any other questions? All right, we'll stop here and I'll see y'all on Friday, God willing.
Thank you. Have a good day.
All right, y'all have a great afternoon.
Have a good day.